So this is the beginning of chapter 13, and chapter 12 was mostly about liquids and how they behave. Chapter 13 is about solutions. So a quick recap of some definitions that are going to come up a lot that we hopefully learned last semester. The solute is the material being dissolved. So if you have salt water, this would be the salt. Okay, the solvent, hope if I could write legibly, sorry. The solvent is the material that dissolves the solute. So if you had salt water, if salt is the stuff being dissolved, the water would be the solvent. It doesn't have to be water, but a lot of times in Chem 1 and Chem 2 it is. If you take organic, it almost never is, and there's millions of other solvents to choose from. And if you have the solute dissolved in the solvent, then you end up with a solution. Okay, so solute dissolved in solvent. Okay, so one of the very first things we're going to do in this chapter is talk about the idea of concentration. How much solute is there in the solvent to make this solution? And we have talked about molarity in previous, like last semester, there's previous videos about this. I'm gonna recap it real fast, but then we're basically gonna talk about a bunch of other options. So molarity is kind of the gold standard. It's the one we use for almost everything. Okay, it is abbreviated as a capital M, okay? M is a ridiculously popular letter. So any of you who last semesters got in the habit of, instead of writing MOL or MOLE for moles, you just wrote an M, you're going to have to unlearn that real fast because it's going to matter a whole lot in this chapter, in the rest of the semester, really. Okay, so molarity, we've seen this before, but it's moles of solute, the one being dissolved, per liter of solution. Okay, so it's the amount of solute in the total volume of solution, not the amount of solvent, the combination of the two, because the solute and the solvent both have some volume. So added together, that's what the solution's volume is. We've seen this before, we've used it a lot. I'm not gonna make a big deal out of it. The one thing I will point out is that all of a sudden in Chem 2, molarity, the unit is M, but it also starts getting abbreviated as a bracket. I don't know who thought this up, and I don't know why nobody ever teaches it in Chem 1, but if you had like a 0.3 molar solution, this bracket kind of means concentration. When we talk about rates of reaction, which is an entire chapter we're going to see soon, this is the type of stuff, this comes up a lot. So I just want to offhandedly mention this. Not going to matter much in this chapter, but I at least want you to have heard of it. Okay, one of the most common ways to talk about concentrations, especially if you're in like the manufacturing industry. So if you're ordering chemicals from a chemical company, the next thing I'm about to write on here, or about to talk about, is the most common way that concentrations are written, because it's the easiest option for them. Okay, so this is percent by mass, and this is slightly confusing because last semester we talked about something called mass percent. This is not the same thing. Okay, this is usually abbreviated as percent weight over weight, so it's W over W. Okay, that's how it's usually written on on the side of like a bottle. Okay. So let's just look at an example. So let's say we have a 35.7% weight H2SO4 solution, and it's in water, so it's aqueous. This is useful information. What this tells us is that if you had 100 grams of this stuff, of the total solution, 35.7% of it, 35.7 grams of that total 100 would be H2SO4. So here's the problem. There are basically two interpretations. I just talked through the first one, and it's the one that makes the most sense to most people. But the other one is also useful. So if you have 37.5% weight of H2SO4 dissolved in water, so it's an aqueous solution, the most logical way to interpret this is that you have 35.7 grams of H2SO4 for every 100 grams of solution. Okay? There's nothing wrong with this interpretation. It makes sense as being 35%, because 35.7 divided by 100 is 35%. Okay? But here's the other option. Okay, so this is one option. The other option is still 35.7 grams of H2SO4 on top, but if we assumed we had 100 grams like we did over here, that 100 grams is made of both the solute and the solvent, and we know the mass of the solute. Okay, so the difference between these two numbers would be the mass of the solvent. So if you take 100 minus 35.7, you get 64.3 grams of water. Okay, so this is the solvent. I guess I should explicitly point that out. I will tell you that 9 times out of 10, this is the more useful option, but there are situations where this version is useful and it matters a lot. Okay, so let's try an example where we use the first one, and then we'll see an example of the other one later. Okay. So let's try an example here. Let's try that same example. We want to know if you have a 35.7% weight H2SO4 solution that is aqueous. We want to know what's the molarity. Okay. So I guess I probably should point this out. This is why this is super easy for manufacturers. What this tells them is that if you suppose you were going to make 100 grams of this stuff, you would weigh out 35.7 grams of H2SO4, and then you would fill it up until the total mass was 100. The end. Super easy, takes no thought whatsoever. You don't have to worry about densities, you don't have to worry about moles, you don't have to worry about the periodic table at all. Okay, which is why this is super common. But the problem is this is really not useful for almost anybody. Molarity is super useful, but molarity is temperature dependent, which I guess I probably should point out here. Okay, this is going to be a big deciding factor of when this is useful. Okay, so what this means is volumes expand and contract with temperature, and since there is a volume component to this, it is temperature dependent, whereas percent by mass is not. These are based on masses. There is no volume component to this. This has a volume component. So in order to convert this, we would also need to know the density. I would have to give it to you. I do not expect you to just know the density. Okay, so for this example, we're going to say the density is equal to 1.17 grams per milliliter. Okay, this would have to be given information. So, in terms of how to interpret this, molarity is in volume of solution on the bottom, so the one that is in terms of mass of solution on the bottom is the most logical plan. So we're going to start with this interpretation. So we have 35.7 grams of H2SO4 divided by 100.0 grams of solution. And essentially we're just doing a unit conversion. We need this converted to moles and this converted to liters. We're doing 2 unit conversions at the same time, but it's still just a unit conversion. So to convert from grams to moles, we grab a periodic table. It's H2SO4, so we add up 2 hydrogens, sulfur, and 4 oxygens. And the value comes out to 98.078 grams per mole of H2SO4. Okay, our grams cancel out. We have moles of H2SO4 on top, which is exactly what we're solving for, so we're halfway there. The other part, we need to convert from grams to liters. We do not have a direct conversion for that, but we can get from grams to milliliters using the density. Because grams is on the bottom here, we're going to want grams on top. to be a G, sorry. So 1.17 grams per milliliter. Grams will cancel out and give us milliliters. We're looking for liters, so there's 1,000 milliliters in a liter. Basically, since this milliliters is on bottom, I put milliliters on top to cancel it out. If we canceled everything out, which we kind of did, we have moles on top, liters on bottom, so we did a good job. And the concentration comes out to 4.26 molar H2SO4. I will tell you that if you ever work in a chemistry lab, this comes up almost every day, because every bottle you grab off the shelf is in terms of this, if it's already a pre-made solution, and you almost always need it in molarity. So this type of conversion factor matters a lot. The reason we can ignore this temperature dependence is because density is temperature dependent. So on the bottle, it'll give you a density, but it'll tell you it's that density at this temperature. If you change the temperature, things get really complicated, and that's beyond the scope of what we're worrying about right now. Okay. So, not a big deal, but this is how you convert from percent by mass, or percent weight to molarity. Okay. I briefly want to mention the other two options. Percent weight is the most likely, but it's not the only option. There's also percent by volume, where everything is in terms of volume. And this is percent V over V, for volume over volume. Okay. So if you ever work in like a biology lab, a lot of times to clean the tables to help kill any bacteria that might be there, they use 95% ethanol to kill everything. Okay. The other 5% is not water, it's actually methanol to make it poisonous to drink, so we don't have to pay the shipping tax for booze. Okay. So if you have a 95% V over V ethanol solution, what this means is that you'll have 95 milliliters of ethanol per 100 milliliters of solution. And yes, you could use the other interpretation to say that there's 5 milliliters of methanol or whatever it is, but this one doesn't come up a whole lot. We don't really need to ever convert this to molarity. We just live with, oh, it's 95%, great. Okay. The other one that comes up is kind of a combination of the two. It's percent by mass over volume. So, since mass is represented as weight and volume is represented as V, this is percent W over V. I guess, in theory, there also could be V over W, but we literally never do that. Okay, if you're ever working in like hospitals, like or in a medical setting, an example of something that works like this is saline, basically a salt solution. We will learn later why you can't just pump pure water into people's veins and not have the cells rupture. But if you grab a bag of saline, it's essentially a very low-level salt water solution. So an example would be like 0.92% weight over volume sodium chloride. Okay, you could pump this into somebody's IVs, and it would be similar enough in salt concentration to be similar to what the blood has to offer. And same general idea here. You could visualize it as 0.92 grams of sodium chloride per 100 milliliters of solution. Your units are dictated by whether it's mass or volume. Okay. This top one comes up the most often. Okay, the percent weight, but I at least wanted you to have heard of these other two. Okay. I'm actually going to stop there and we'll do this as a two-part video. All right, thanks.